Hello everyone. This video is about logistic growth, and I want to reference the equation that we started with here before the schools closed. We were talking about exponential growth, and a logistic model actually it begins with the shape of an exponential curve, but then it begins to level off. And what's happening here is we have a horizontal asymptote at something called the maximum carrying capacity. And if you look at the slope here, the slope is almost zero here, and then the slope gets larger and larger, and then the slope starts tapering off to zero as you start approaching this capacity. So our equation that we start with first actually looks like this. We still have the constant times p, but as p approaches m, this factor gets closer and closer to zero, and then the derivative is going to get closer and closer to zero as our model, as our graph here suggests. Now I'm going to streamline this a little bit, and then I will fill in pieces in another video. But if you remember separating the variables, we would do the same thing here. It turns out to be a little bit more complicated because we have a p here and an m minus p. But what we end up getting after we separate the variables and we integrate, we get an equation that looks like this. And this is the equation for a logistic model. Now, in number 31 and 32, I realized that I had chopped off the directions that were in at the bottom of the previous column, and I apologize for that. But here, the directions say we're supposed to identify K and M, the carrying capacity, and then we're going to use this equation to approximate what the initial amount of P is. So in number 31, we're talking about a population of rabbits, and then in 32, we're talking about the spread of measles. But we can see from our equation here that M is equal to 1,000. So we're talking about 1,000 rabbits here as a maximum carrying capacity. And then here we have the rabbits, this is for the rabbits, and this is for the number of people who have, or number of students who have measles. And so M is 1,000 here, and it is 200 here. Now, once we know that the M is 1,000, and here the M is 200, then we can set up an equation to solve for K. So what I'm going to do is take M times K, in each case, M times K, and I'm going to set it to be the coefficient of T. So when we do that, in number 31, what we would get is 0.7 equals 1,000 K, and here the coefficient is 1, so we have 1 equals 200 K. And what that tells us then is if we divide here by 1,000, we get 0.7 divided by 1,000. We get a K of 0.0007. And then here, if we divide, we get 1 over 200. Now, you can leave your answer as 1 over 200, or if you wanted to convert it to a decimal, that's fine. But we get 1 over 200. Now, the second part is we're going to approximate what P is. So if you take P is initially, when T is 0. So what I'm going to do is plug in a 0 here, and then I get e to the 4.8 minus 0. And then I'm going to take 1,000 divided by 1 plus that particular value. So now, if I do this on my calculator, I will get e to the 4.8 Okay, so we take e to the 4.8, and then I'm going to add 1 to that from here. And once we get that, we get about 122.5. Now, that's the denominator of our fraction. So if we take 1,000 divided by that, then we get about 8. So 8 is p sub 0, so that means originally that we would have about 8 rabbits. Okay, there's about 8 rabbits initially in that situation. Now, for the second one, we're talking about measles. So now I'm going to take 200 and divide that by 1 plus e to the 5.3 because t is 0 in this case. So now, if I'm going to do this one a little differently. I'm going to take 200, and then I'm going to divide that by 1 plus e to the 5.3. So I just did this a little bit differently. Notice that I have the parentheses here for the exponent. I also have parentheses for that denominator. And then that gives me about 0.99. Now, we're talking about people that are students that are infected by measles, and so this would be about 1 person initially. So this would be 1 student.